Okay, so for problem number 7, we've got a non-conducting ring of radius r lies in the on the yz plane, and the ring is charged with a positive charge. So we've got positive q here for the entire ring, and we need to find the x component. So if we were to focus on a position on the x-axis, and I'm trying to find the x component, then I would want to take a small subsection of charge. Let me make this thinner. So a tiny subsection of charge in a piece of this ring, which would be dq, and that dq would give us the electric field pointing down and to the right, and that would be dE, just a small section of charge. We'll do the same thing on the opposite side of the ring, another small, and usually the notation is lowercase q. It really doesn't matter, but big Q to represent the entire charge, and then little q, little dq to represent the little piece of the charge. So that would create an electric field in this direction because it's positive. And that again is a small section of the electric field. So in order to find the x component, we can see here that the y component actually cancels out. If these are perfectly symmetric, which they don't look like it, but the y components cancel out, which is part of part B. So let me just clear that out. And then all we have left is the x component. So what I'm going to do to get the x component is I'm going to create a theta here, and I know that cosine theta is going to give me the x component that goes out in, let me use a different color, the x component that goes out in this direction for one electric field, and the x component that goes out in this direction from the other electric field. Now, if we did that all the way around this circle, we would get all the electric fields to add together, all the little pieces of the electric field to add together, and that would give us the net electric field of the ring. The second part of part B is asking about the z component. The z component comes out of this side of the ring. So if we were to look at a subsection here, so let me get rid of that line, and that were to go into the the position on the x-axis, we could see that the z here would cancel out if we were to take a subsection on the equal and opposite side and come back to P. They would end up canceling out on the z section. It's hard to represent it in a 2D diagram, but you would be able to notice that the z component, when you're taking the positions on the positions of the ring on the z-axis, would also cancel out, and it would be the same all around the entire ring. So let's focus on the x. We know that EZ is also equal to 0. So let's calculate EX. This is part A. So the small component of DE in the x direction, so the entire electric field is composed of the x component because everything else cancels out, is K dq, because it's only a subsection of the charge, over r squared. Now we have this r here, which is the radius of the circle, but r squared is really the distance from the piece of charge all the way out to the position that we're looking at. So we need to figure out what that charge is. I always kind of define the x position to be x, and the radius is generally given to us as capital R. So based on the Pythagorean theorem, this is a 90-degree angle. If this radius is capital R and this distance on the x-axis is x, we just do not r squared, but r is equal to the square root of big R squared plus x squared. And that can be substituted in for this guy. And then, of course, we're looking at the x component, so that's cosine theta. So let's start doing our substitution. I'm going to substitute the r squared plus x squared in for r squared, because the square root squared is just the function. And then cosine, this is interesting because we have this angle here, which we know is going to be equal to, if it's coming from the top, then we know that the angle here is also theta because it's symmetric. The pieces of charge we're taking are on opposite sides of the symmetric ring. So the thetas are going to be equal for the top and the bottom angle, and then based on, I think it's called interior angles, this angle has to be equal to that angle. And the reason why I am trying to find that symmetry is because cosine theta for this theta here, since it's equal to this theta here, is going to be equal to x over, which is adjacent over, the radius. So essentially, even though we're focused on this cosine of this theta is going to be the same. So it'll be x over the square root of r squared plus x squared. So that's what I'm going to substitute for cosine. Okay, so let's bring all our constants together and our dq to the outside. R squared plus x squared is the same as the square root of r squared plus x squared squared. And if I put all of that together, I get a denominator of r squared plus x squared to the 3/2. And then kx dq is what I have in my numerator. And let me actually move the dq out here, because when I start to integrate, I can integrate on both sides, this dE and this dq. And since I don't have any q's in my function, then I can, if it goes from 0 to the total net charge of my ring, which is q, then I end up with, let me just get some space here. Then I end up with E is equal to kx over r squared plus x squared to the 3/2 of q from q to 0 or 0 to q. And then obviously that simplifies down to kx big Q, or the total charge of the ring, over r squared plus x squared to the 3/2. All right, so this is our electric field along the x-axis. That's my answer for part A. Find the distance which the electric field is a maximum. So anytime we're trying to solve for a maximum or a minimum, we're trying to solve for the derivative of that value. And we're going to set that derivative equal to 0. So let me clear out some of this space, and we can take dE over dx equal to 0. So this is our E function, which means that d over dx of our E, which is kxq, over r squared plus x squared to the 3/2 is equal to 0. And even though we do have an equation for the quotient rule, that is much more complicated than doing the equation for the product rule. So I'm going to turn this into a product by rewriting it as kxq times r squared plus x squared to the negative 3/2. They mean the same thing. Okay, now the product rule. Go ahead and look this up if you don't know it. I did teach it in class as well, so I'm not going to teach it again in the notes, but I'll walk you through it as I go. The derivative when you have a initial function multiplied by a second function is the initial function times the derivative of the second function. And I want you to notice that this is a function of x within a function. So I'm going to take the outside function first. This is the chain rule. I take negative 3/2 multiplied to the outside, r squared plus x squared, and then the power of negative 3/2 I have to reduce by 1, so negative 5/2. And then I have to take the derivative of the function within the function, which x squared's derivative is times 2x. So this is my derivative of g. And then I have to add it to the derivative of the first function, f of x, which in this case, the derivative of the first function with respect to x is just our constant k times q. And then the second function as is, which is r squared plus x squared to the negative 3/2. And this whole thing, that's a negative, is equal to 0. I don't like that. My parentheses here is not a bracket, so let me redo that. Okay, so let's start simplifying things. I have this 2 down here and this 2 up here is canceled out. I have an x and an x, which is squared, and I get the negative 3 as my constant, k q x squared times r squared plus x squared over negative 5/2 plus kq times r squared plus x squared times negative 3/2 equals 0. Since this is negative, I'm going to add that to the other side so I don't have to work with any negatives, and I end up with kq r squared plus x squared over negative 3/2 is equal to 3kqx squared times r squared plus x squared to the negative 5/2. And simple algebra, but more work. We have to reduce. I'm going to take my r squared plus x squared of one side and divide it to the other side. And then I know that if I have a function with an exponent on top and the same function with an exponent on the bottom, I can simply subtract them. So negative 3/2 minus a negative 5/2 gives me a positive 2/2. And since it's positive, it's in the numerator. So I end up with just r squared plus x squared to the 2/2, or r squared plus x squared. And that's it. On the left side, I have a 3x squared, and then bring together my common values. R squared is equal to 2x squared, and I want to isolate x because that's what I'm solving for. So I end up with x is equal to the square root of r squared over 2, or r over the square root of 2. So this would be either a max or a min. Since they're asking us for max, I'm assuming that's the max, but we can go ahead and solve for this as we analyze the graph. So let me erase a bunch of stuff, and then we'll get into how we can analyze this graph a little bit more. Next step is to find the maximum value of the electric field. Since I know my electric field equation here, and I know my x here, we can start plugging in values. Now, I mentioned that we don't know if this is a max or a min. I also took the square root, and anytime you take the square root, you have a plus or a minus. And when we plug in this value into the expression, we're going to see whether it gives us a positive or negative value, which lets us know what we're working with. So in this scenario, my question part D is finding the electric field at R over root 2. We'll start with a positive, which is equal to K R over root 2 times Q, all over R squared plus R over root 2 squared to the 3/2. And then I end up with KQR. The root 2 I can bring down into the denominator. And then this function here is going to end up as R squared plus R squared over 2 to the 3/2. And to get common denominators, I multiply top and bottom by 2. And I end up with KQR over root 2. This gives me times 3 over 2 R squared to the 3/2. To take 2 of the root 2's inside the expression and pull it out. So I'm going to take root 2, and then I'm going to multiply 3/2 R squared, because that's 2 of the square roots being pulled out. And then one more square root would be root 3 over 2, and then the R squared would just end up being R on the outside. So simplifying all of this out, the root 2 can cancel. The R here can turn this into a cubed, and I end up with 3 root 3. Actually, I end up with my numerator, which is KQR, all over 3 over 2 root 3 R cubed. And then from there, I can simplify this R down to that R squared. I have a fraction here, so I can multiply the 2 up on top, multiply it by the reciprocal. I get 2KQ all over 3 root 3 R squared. And for problem number 7, I don't get the right answer, but let's see what happens when I take this K and substitute 1 over 4 pi epsilon naught. So 2Q all over 4 pi epsilon naught times 3 root 3 times R squared. This reduces down to 2, and I get Q over 6 root 3 pi epsilon naught R squared. And that's exactly the answer in part D. Okay, so first thing we want to do is R over root 2 is maybe somewhere around here. And we've got some value, and all the values are positive. So we're going to have some value here of Q over 6 root 3 pi epsilon naught R squared. Let's think about the position here at x equals 0. If I look at my electric field equation, if x is equal to 0, everything ends up canceling out. E is equal to 0. So that would be this position here. Now, I had a positive and a negative R over root 2. So I know that if I were to put a negative value in here, we'll see what happens. I have a negative r over root 2 for x, which makes this a negative in the numerator. A negative r over root 2 in the denominator keeps this positive, and so the expression then is going to be the same. At x equals negative r over root 2, that's going to give us e is equal to the negative of q over 6 over root 3 pi epsilon naught r squared. And so in that case, we've got somewhere here at r over root 2 some sort of minimum. And then we always want to think about what happens when x approaches infinity. And as x approaches infinity, this value goes to infinity and this value goes to infinity. You might have to simplify things down to figure out what really happens. But if we look at our electric field, if I were to move this p position all the way out to infinity, we know that the electric field, it decreases by a factor r squared. That's just part of the equation. So it's going to decrease and decrease and decrease closer and closer to 0 as it goes out to infinity. So we're going to have some sort of asymptote as it goes out to infinity. It's going to approach 0. So in this scenario, it's going to look a little something like this. It'll increase to its maximum and then decrease exponentially to an asymptote of 0. Here, it has a negative electric field minimum at r over root 2, and then it decreases, or sorry, the magnitude of it decreases, but it actually gets less and less negative and approaches 0. So the graph isn't perfect, but it matches what you see in your answer key.